Hello everybody, we're going to start the third week of the course, and so today, after talking about general things and then data structures last week, we're going to talk about how you actually interact with some of these data structures. And today we'll plan to get through searches, and if we have time we'll also talk about how to do sorting, and then we'll see where we go from that. So the first type of search we'll talk about today is a binary search. It's relatively straightforward, I hope, but it can kind of be instructive about the ideas of how we do things and some conversations we can have about it. So we're going to start with an array that has already been sorted. And so next week we'll talk about how to do that sorting, but for now we'll just assume it's sorted. And say we want to find some value in this array, and the only thing we know about it is that it's sorted. If we don't know what any of the values are beforehand, what would be kind of the first step we could take in finding a value? So what would be like one way to start?
Just go through starting at 1 to 7 and check each value.
Yeah, so you can start doing a search all the way through. And what would the complexity of that be?
Oh, n?
Yep. And so this is searching through every position linearly. We just go up by one every time, and it has a linear complexity. But this doesn't take advantage of the fact that it's sorted. And so how can we take advantage of the fact that we've sorted the list? How would you perhaps modify this?
Go to the center first, and then decide if you're higher or lower,
Yeah.
left or right.
And so this is exactly the procedure that will lead us to binary search. So you calculate some center, some position, and you say, all right, I'm here. Is the value I'm looking for the value I'm at? Or is it higher? Or is it lower? And depending upon what that is, you either go left or you go right. Let's say we're looking for the value 1. And so how will this work out when we go over here? What do we do next? We've decided we're going left.
Search the new middle.
Search new middle. Alright. So now move our middle pointer to 2. And then from here, we say we're left or right. We gotta go left. We go left. There's only one value over there. This would be our middle value if we were taking that middle. And so we get the 1. We get the value we're looking for. And the question is, how many steps did we have to take to get here? And how many steps will we have to take in different situations? So what's the most steps we could ever take with this algorithm before we find the correct solution?
3.
In this case.
In this case. But how will this change as we get bigger and bigger?
So log n.
Yeah, it's going to end up being log of n. And why is it log of n?
Because it cuts the number of possibilities approximately in half each time. So
Approximately half?
well, it depends on if it's odd or even. So, but yeah, that's just being amazing. But,
Very close. So it would be exactly half or within sampling error. Yeah, so because you have half of it on one side, half of it on the other, and you're always excluding half of it every time, it'll have, oftentimes you'll say it's logarithmic, but it's base 2 because you're dividing in half. And so, sadly, for the most part, you can't really ever beat binary search. Really, the only types of searches that you can do with a better complexity are ones that are at constant time. And so that pretty much gets you down to hash maps, so the only things that, on a normal case, really ever beat binary search. And this is an algorithm that comes up a lot. Anytime you can keep your data in sorted or order, binary search is the reason you do it. Because it means that you can find everything in order very quickly. That's not strictly true. Sometimes you want to process things in order. But if you're searching, it's very handy to have it in binary search. Because every time you want to look something up, it's order login. And if you need to try and find something, or if you need to pay some cost to keep it in order, it's often worth that cost if you're doing a lot of searches on it. We'll talk about that more next week. And so actually we're going to do something a little bit different from what we've done the last couple of weeks. We're actually going to turn this into a bit of an algorithm. Sorry, question?
So, why would you not just use hash maps like all the time?
So,
It's generally faster.
it is, but it has additional costs as well. And so you have to store additional space for having the kind of level of misdirection of saying, I have a key, that key gets transformed into something that you use as an index, and then that index points you to somewhere else. And so all that level of kind of misdirection has a cost. It's also harder to think about often, and it also doesn't deal as well with, if you have something that's kind of scaling over time, it's difficult to have to deal with collisions. And so you can often use them, they're often great, but they have a lot of kind of complexities that we really didn't go into, and they're just not perfect for every situation, particularly if you have everything already in order.
So creating and I guess maintaining the array or the hash map could potentially take longer.
Yeah. Typically it's an issue with growing the arrays. So like once you start trying to put more and more items in, more and more things start colliding. So you need to take kind of special efforts to have that not happen. Yeah, and then also it's the issue of space. Anytime you have a hash map, you need to have enough extra room that things won't collide, or have some way of dealing with that. So you always, almost always need to allocate additional extra space in a hash map. And so by doing a binary search, you don't have to allocate that extra space, depending upon how it's set up. Yeah, there are a lot of times where you can use a hash map to kind of accomplish some more things. And so we're going to actually talk through two separate ways of doing exactly this algorithm. Because it's a simple enough algorithm, we just walked through the idea. I hope everybody can understand it. Anybody have any questions on kind of how it works? But we're going to walk through it in two different ways. One is going to be a recursive method that does this, and the other is going to, actually we'll save this to the next step. Because we're actually going to advance the slides one more time and look at this on a tree. And so we're going to take exactly the same data structure as a binary search tree, and then we'll talk through both of the algorithms on that. Both of the algorithms also work on this kind of array-based implementation, but in some sense they're a little easier to talk about on a tree. So we'll turn this into a binary search tree, where that's the properties we talked about last time, where everything to the left of something is less than it, everything to the left of this node is less than that node, and everything to the right is greater than or equal to. And so it goes 1, 2, 3, 4, 5, 6, 7. And one thing that you can note from having done this, if you have a sorted array, you can turn it into a binary search tree in order n operations, just one for touching each element in there. Because you already know kind of how many levels it will have to be able to fit this many elements. And you can just say, well, there will be an item in position here. I can just give it this value. And so there's a lot of kind of tricks you can do converting between things if you already have some structure that you know about them. But we won't talk about that too much. The search operations for doing a binary search tree, it's named a binary search tree because it allows you to do binary search. very simply. Every time you want to make a choice, you say, am I looking at this node? Well, no, then let's go to the left. Let's go to something that cuts out about half of the tree. And so we'll cut off everything over here. Then you say, well, let's cut off half the stuff again. So we'll remove this. And we're left with the case we were looking for in this example. With the binary search tree, you need to be careful and pay some cost to keep it roughly balanced, so everything at the same depth, which would be similar to the cost, which is equivalent to the cost of keeping your array in sorted order. And so one way or another, whether you keep a sorted array or whether you keep a binary search tree that's balanced, you still have to pay some cost as you add new items to kind of keep everything in a good spot. And so we're going to write two functions. We're going to write, it'll use Python, but it should be recognizable in its syntax. You can do it in any other language. We're going to define a binary search function, and then we'll come back here then we'll define a version that's a recursive version of the same algorithm. And so our function is going to have two inputs. One is going to be the tree itself. So we're going to do that by passing in a root node. The other is the target value that we're looking for. And so we'll walk through how to write this algorithm first in kind of a stack-based method that just tracks the current node that we're on. And so how do we translate this procedure of asking if the value is left or right into actual code? Like, what do we actually have to check if we're given a node? And we want to see, is this what we're looking for?
Compare value of node to target.
Yep. So if root, we'll assume these all have a value, a left and a right. That'll be helpful to know. That's not actually a definition, but good enough.
Are left and right the addresses of them?
Yes, they're this relationship, something that maintains a reference to the two children. And the references can be none, which is something we can check for. Okay, so we have instantiated this as the thing, or if we find the target we're looking for, then we can return this. And often, here we've talked about the binary search looking for a value and that number being the only thing we're storing here. Oftentimes, you're storing some kind of value of interest in here that you're sorting based on, but there's a lot of other data associated with it. And so often you'll have an object that maintains all the other stuff you care about, but you have some sort of organizing value that you want to keep track of. So for example, like if you have people's driver's license, it says you can organize them all by birth date. And so you can search based on the birth date, then when you find the one you want, you can pull it out and you have all the other information with it. And so in this case, we're going to return the node we're looking at when we get to that case. I should look more space in there. It's a good little squish when we're done, but it'll be okay. And so, what happens if we don't find the value we're looking for? So the root value is not, or the value of the node we're looking at is not the target.
So it's bigger than the target.
Yep. And when we do this, what do?
Right or left?
Do what to?
Yeah. So do you set root equal
So this is where we get a choice. We can do two different things. And we'll talk about then how they're equivalent. We have one suggestion, which is that we can call this function again using the, show them right next to each other here, we can have two different values. We're going to have the, so I'm actually going to write all this out, except with a much shorter name. And hopefully it shows up on the camera. So now, we get to make our choice. This will be binary search recursive version. This will just be the binary search version that's not recursive. For the recursive version, if the node value is greater than the target, we just call the function again. But this time, we pass it the right child. And we keep the target value the same. And so we'll walk through what that does in a minute. The other one is that we get set the, if we're kind of going through in what's more of a stack-based or kind of state-based method, we just set the root, in this case I'm using notation, to be equal to the old root's right value. And then we can do kind of the opposite situation as well. Okay, and so And so there's something missing in each of these cases to make it work. And this is one spot where the algorithms diverge a little bit. So what do we need to make the binary search version work?
Needs to do it again somehow.
Yep, you need a loop. You need something that keeps going until it reaches some stopping condition. And so in this case, you can just go in Python, while root would work, because none is not a variable condition that will stop. But you can also test it explicitly. While root is not none. Keep doing this. And it will keep looping through until eventually either the root value is none, or the root value is equal to the target and we return the root. And so if we eventually get to the root value not being none, we break out at the bottom, and what do? We can return some control value like none. And so what do we have to do to make this binary search version work?
Check to see if the left or the right is none, like if it doesn't have a left or a right child.
And so we could do that with how it's written. We don't actually need to. We can add in a different check. And so it's somewhat similar to this one over here.
You just check if node is none.
Exactly. So yeah, we just check the thing we're looking at is none. Because that'll be the same case where the child that we passed, or the child that we're investigating next has a value of none. And so we can just say, unfortunately this will get really squished and break proper syntax. So if node is none, return none. And then both of these will work. And so they have very similar kind of form to them. They have very similar kind of effects. And this is something that will always be true. If you can write a recursive version of a function, you can always write a non-recursive version that uses a loop or a stack. And oftentimes it'll use both a loop and a stack. And we'll kind of talk through some more examples of that as we go on with the class. But what are some differences between them in terms of how they use space or how they use time and kind of complexity and cost of the algorithms?
Recursives can use more space
Because?
because it keeps every time you call itself, it's gonna add that much more space.
Yes. And also one thing I failed to do here was in a recursive call, you have to return the value of the call, which I forgot to do. And so we didn't talk a ton about stacks and how they work for calling stacks. But what this is doing is every time it's investigating part of the, or one of the values, part of the tree, it says, aha, here is the root value is, I'm going to draw this a little bigger so people can actually see it if they're looking. The first node we're going to look at is 4. So we're going to say, aha, does 4 have our target? Well, in this case, it doesn't, because our target is 1 again. And so then we kind of walk through this, and we're just going to call a function, which is going to take up a little bit more space on this calling stack. So then it's going to look at node 2, it's going to compare to 1, and it's going to say, is this the value? Well, no, it's not. And so we're going to look at node 1 finally, and look at case 1, and it's going to say, aha, finally we made it. If this were to be kind of 0, we would also look at 0, or we would have none, sorry. We would be looking for 0, and that would eventually kind of also return. And so, one way or another, we're always going to stop, but you have to store all the information about where you came from. And then this return statement happens, which returns a value to this function call. And this function call returns a value either to one of these function calls, or to the program that originally called this function. And so you have to dedicate some space to every time you made a call. So this is a cost that you always have with recursion. It's something that you can always optimize out of your algorithm, but it's often very easy to explain an algorithm in a recursive way, and can sometimes be very tricky to explain it in a non-recursive way. And so it's helpful to be able to think about algorithms in both different ways. And sometimes these will be easier to write down, sometimes these will be easier, and it's just something worth thinking about and keeping in mind. Yeah. And so for that, we're actually going to spend a little bit more time talking about recursive calls, and then we'll see another example where you can write an algorithm in both different ways, and then we'll move on from there. And so there's two types of cases in a recursive program. We have this top half here, and we have this bottom half here. What's different about the top and the bottom half here? In terms of what they do. That's still a terrible answer. Let me see if anybody can get it that, and then I'll give you more hints.
The top's not recursive.
Perfect. So this bottom half is recursive, as you're saying, it's an indication of that. And so this is often called the recursive cases. And so generally that's anything that calls itself, either directly or indirectly, will be a recursive case. This is something you have to watch out for because it could go endlessly. It could just keep going and going and going and never stop. So eventually, you have this non-recursive case, that this is what actually returns a value. If you never hit this, it'll never stop. This is called a base case. And it's important to make sure that whenever you write a recursive algorithm, you have a base case. You have something that says eventually this will return a value that's meaningful and everything will be finished. And then these will then propagate back up through the recursive cases all the way out of the function to get to the code that originally called it. So anytime you're thinking about a recursive algorithm, remember to think through all the base cases and all the recursive cases. And remember to think through what happens if you find your values, if you don't find your values, and whatever task-specific parts of that are required. Does anybody have any questions on this?
So that's at the end says return node, right?
This one says none.
None.
This one. So this is the case where we did the root became none. And so we broke out of the loop, and we got all the way down here.
Okay. So how do you actually get the value? Oh, it's because it's return root. Okay.
Yep.
Nice.
And so this is kind of that alternative
Yeah.
alternative base case in the loop-based version. As when you find the right target, you just return it directly, and that matches over in the recursive case.
How for the recursive case, how could you make it so it doesn't generate the stack?
Turn it into this algorithm.
Okay, you can have it take out the bottom memory.
Well,
That could be kind
so let's think about it. So what happens when you get down to this bottom place down here? Like you've called this function 4 or 5 times. If you overwrite the memory, where does this function return to?
No, it's not the right place.
Yeah, it returns to nowhere. And so you need to kind of track where things are. If you got really kind of fancy, you could design something that for recursive calls, it puts it in place of these are called stack frames. It takes the place of the stack frame that came before. I believe this is known as end recursion, and it's actually implemented in certain kinds of languages that are usually called functional programming languages. I think like Haskell is an example. Haskell, not Pascal. And in that case, it will replace that last element, if it can, with just the current stack. And so there are programming languages that are designed to do that, so you can spend more of your time writing recursive functions that are often easier to work with. But for most programming languages, it's not an option, easily. It's easier just to switch over to actually writing it directly as a...
Instead of returning node, could you just have it set the value of a global variable? And then it doesn't have to go through everything? Okay, is that the same as that? Yeah.
That's what you're doing over here.
Okay.
And so yeah, these things are equivalent. You can switch between them in different ways. And yeah, there's multiple ways to make this conversion. This is just one that I used.
So is there an obvious flaw to using a while loop then?
Generally speaking, no. Not that I'm aware of, at least. The cost is typically that they're more complex. I can't think of a good one off the top of my head, but at least the rationale is that there are some things that you can write a recursive case for in 4 or 5 lines, or like 100 lines or something. While the equivalent non-recursive case, because you have to track kind of what you've done, what you haven't done, can take much more time and space. Because it can be much harder to think about. You might need to use 10 times as many lines of code. Although here they're pretty equivalent. They are equivalent. So, with that, we're going to move out of binary search, which is something you can only do on sorted arrays. You can either a sorted array or a sorted data structure, because it takes into account the fact that you can safely exclude everything over here. Thank you. But you can't always do that. There's lots of cases where you don't have sorted data, or you have partially sorted data, or the sorting is kind of messy, and you still need some way to interact with it. And so for that, we're going to talk about depth first and breadth first searches, which are very similar to one another, which is why we'll talk about it. So I'm going to erase these parts of the board, and then we'll do this again. And I'm actually going to redraw this over here, so we have a little bit more space on this one board. And so we'll start talking first about depth first search. And we'll do the same trick where we define, the same thing where we define a method for each one of them. Does anybody want to take a stab at? So, for setting these up as breadth versus depth, how might that interact with this data structure? If we have a tree data structure, kind of how might, what part of the graph, or what would it mean to keep something at the same depth? Sorry, it's Jeff would ask that question. I'm just going to say what it means. So if you have depth first search, it means you're going to look all the way down the graph as quickly as possible. And you're just going to kind of search the deepest things you can as quickly as possible. If we have, and that'll make more sense once we write through the algorithm. In contrast, if we have breadth first search, we're going to set it up so we look for things closest to the node that we were starting with. And so we'll start with this guy, and then we'll go to the closest one, the other one that's really close, before we get to any of the leaves. And so you're doing things where you're kind of spanning out and staying as close to the point as you are, or as you could, instead of doing depth first search, which runs all the way to the end and kind of tries to go as far as possible every time. And if that didn't make sense, hopefully it'll make more sense once we see the code. So we'll start by writing an algorithm that's depth first search. This one actually will use a stack directly. And this will be node, this is target. And then we'll also have and so how do we, if we wanted to start by searching down as far as possible, actually we're going to do it with the recursive algorithm first. That's often easier to think about, and it is in this case as well. So what's the first step in a searching algorithm? What's our base case going to be for a recursive depth first search? It's the same as last time.
Check if you're
Pardon?
See if you're at a leaf.
Uh,
Isn't that what you did first last time? Or not for recursive, I guess. Well, there's
So-
two things you want to check, if you're at a leaf and if you're at a target. I don't know which one.
Yeah, so what do you, so you're using a term which we haven't brought up actually, which is if you're at a leaf. And that's a common term that people talk about with trees. So what does it mean to be at a leaf?
There are no children.
Yeah, there are no children. But that's still part of the tree itself. And so that's a little different from what we did last time. You could structure your algorithm to check if you're at a leaf, but we're not doing so. We don't need to do so. What did we do instead of checking if we were at a leaf?
I just saw if you were none. If
Yeah.
the node was none.
If you were off the tree.
Right.
If this pointed to somewhere off of the tree, or didn't have a pointer to it, more exactly, then you would say, you know, we were off the tree at that point. So obviously there's nothing in the tree that satisfies our criteria, what we're looking for. And so, if node is none, and what was the other condition that we were interested in?
If you're target.
If the target. So if node is none, or node.value is target, return the node that we're on. And so from here, let's take a step. Say we want to go somewhere else. So we've discovered this is not the one that we're looking for. How do we kind of proceed to search through the tree if we want to get to the leaf as fast as possible? If we want to get to the furthest down point as fast as possible, how would we kind of proceed to make a search? If we're trying to run in a straight line.
Always go the same direction.
Yep, always go the same direction. How do you travel in a direction in a recursive search?
Always go like to the left.
Yep. And what does that mean exactly? So what does it mean to go in a direction? How do we go?
Set node to the address of the new node.
How do we do it recursively?
I'll just call it with the child as the node.
Correct. So we just are always going to call that first search on the node.
Like, doesn't, if it's balanced, it shouldn't matter if you go the same direction or not, right? If
What shouldn't matter how?
it shouldn't take any longer to get to the bottom. It shouldn't take any more function calls if it's a balanced tree, right?
That's true. But the question is, what do you do once you've gotten to the end of the tree?
Yeah.
You'll have to find, and so eventually we want this method to kind of go all the way out as far as it can, but we still want it to be able to hit every node in the tree if possible, or if necessary. And so to do that, you go to pick a direction. You're right, if you had some other reason, algorithm or something, that said which one you tried in which order, that totally would work. But you just need to make sure that you don't kind of go down the left path and then kind of backtrack and go down the left path again and then finally go down the right. You want it to be deterministic in how it does it. And so the simplest way to do it is just always go to the left. But you're right, in this case, if we alternated between them and had some rule for doing so, we could get an algorithm that would do the same, but alternate. And so what do we do with this recursive call? We've made the call, but how do you actually handle that? What do you do once you've made the call? What do you get from making the call?
Right, so that's on the same line as if, right? Or the same variable as if.
More, we're going to need to add something over here, so I left a space.
Oh, okay.
So, but yes, that's a good call. Under the rules of Python, it would have been on the same line, but it also would have been after the return, so it would have been an invalid statement. But more, I'm leaving space over here. Because we need to store, we need to write something there.
You need a return.
Pardon?
You need a return. Or are you talking on the line above?
We might need a return. So why would we want to have a return here potentially?
Because you want to, eventually when you get to the end, you want to be able to go all the way back.
Yep,
Pass
exactly.
the value back.
You want to be able to pass the value back. But if we just return a value here, what happens when we're looking for the value 3?
So it makes up one point.
Oh. You want to do another if statement, see if that's equal to a value or none.
And so the problem that would have come up is that if we're searching for, if we just write return in that little blank spot, we'll walk down this tree, we'll get to 1, we'll say we didn't find it, we'll take a step back here and say, well, we're returning values, whatever comes back up. And so we'll never explore the right branch. So what you actually need to do is you need to store this value in some variable. Being generic, I'll just say x. And you can say then if x is none, return depth first search recursive unknown.write. And if x is not none, down here we'll return x. And so, and as we were saying, now this is something that will handle both going to the left, and when it needs to, it'll go to the right. And it'll kind of do what's called, often described as avenues. And it'll eventually all the way back up to the root, and kind of go down this other branch of the root. And so it'll do that to explore the whole space, and it'll eventually find everything that could possibly be there. And so we can talk about some of the complexities for how this algorithm will run. Yeah, you could switch around searching left versus searching right, but for simplicity, let's talk about it as it's written. How long would this algorithm take to find the value at 1? How many steps? Let's ask that. How many function calls?
Somewhere between n and log n, right? Because in the best case, well, actually in the best case it's constant time. It's like parent nothing or something.
So if it's the root.
Yeah, but like, let's say you find it in like the first branch that you're looking down, you're probably going to take more or less log n time to get there, or log n over 2 time to get there. It's assuming that it's somewhere randomly along that first branch. But the worst case is that it's all the way to the right and you bias yourself to the left. And so you have to go through every single item, and that's O n. So I don't know what the average would be though.
That is the right answer, though. The average, I can't remember off the top of my head, but getting the kind of the best and the worst cases for this algorithm is good to think about. And so if we're in the case where we get lucky and it happens to be at the end of that first trajectory we were looking for, it's going to be log n, not over 2, but because it's the same number of kind of steps you'd take as if you were traversing there directly with a binary search tree. So it's going to be order log n to get there. And so your kind of best case to a leaf and your worst case to a leaf is going to be all the way out of the end, which is order n.
Don't you have to revisit some of the nodes though? If you go, say like 4, 2, 1, then you want to check 3, wouldn't you have to go 4, 2, 3?
So
how
you
am I
don't.
missing something?
Yeah. So the way this works, let's walk through it actually. So what happens if we're searching for number 3? And we're going to build our call stack down here because we haven't actually had a stack yet. So we're in 4. Starting node 4, we're looking for value 3. Where do we go?
First 2, and then 1,
Mm-hmm.
and then I'm not clear where we go next.
Well, so we are on this thing called the call stack.
Yeah, so I guess
What happens when we call this on node 1 with the target?
node 1 with the target. Oh, if 1 is the, what's our targeting, 3?
So yeah, we're in node 1 and we're looking for 3. What do we do?
Okay.
So what happens?
So node is none in that case, is that right?
Nope, the node is 1. So where do we go?
Okay.
So are we in this line?
Not there.
Do we call this line? Or what does x return?
It's going to return 1, right? Or no, it's going to return nothing because you don't have anything in your left node, right?
So we have to add something to the stack because we're calling our recursive function again. So we're putting none onto the stack with value 3.
Okay.
And then we go in here and say, that's nothing. So we return.
Mm-hmm.
And so we have returned none. X holds none. So if x is none, we go in here and we do the same thing on the right. So we actually return off of the call stack. And then we put down what ends up being the same thing, looking in the right child.
Oh, sure, okay. Right.
And now we just return whatever comes out of the right child. And so when we do that, we say, aha, we've returned this part of the right child. And this guy's just returning his right child as the depth chart search result. So we've gone and stepped back to here. And so in terms of the number of function calls, it's dependent on the kind of number of n. Some could probably fairly note that because we're not checking, or because we're calling this on things beyond the leaves, it's actually a little bit higher. But that could be worked around in either end and talked about. You could test for that basically. Yeah, so once you've hit this case, from here we've returned none. And then we go and check the right branch then. And so we don't have to start all the way from 4 again. We just get to start from as far back as we needed to go. And so then we check 3, and we find it. So we return back into 2, we return back into 4, and we return back to our calling function with node 3. And so the, kind of as we talked about, but to kind of reiterate the point, did we ever check node 5? Did we ever check node 6? And so by doing this algorithm, because we got lucky, we found the position we were looking for, we didn't have to check this part of the search space. And so that's the difference between the best and the worst cases. Like the best overall is order 1 because we started at that position. Yeah.
So, I think, is there a reason why we should have the base case be making an additional call given none, instead of just having the base case be if node dot, left, or node dot right, or if not node dot left, node dot right. Right, in other words, not check, like actually going down and calling the function again and just seeing if there are no children.
Yeah.
Because I think I was just trying to think about how to write the second if statement in a way that was a little bit more intuitive, because I had a hard time keeping track of what x actually was representing closer towards leaves, just intuitively, and so I was just thinking maybe if x were representing, if the base case were checking if there is a child instead of checking if it itself is none, would make that any simpler.
You could write that check before you call this one. So you could put an if statement above here and say if node.left is not none, then do this.
Yeah.
And then you would be able to directly do the return. No, you can still not directly do the return. I take that back.
Oh, right. Yeah.
You could say, if there's a left node, do this check. You'll still have to check what the value is out of here. And you'll have to see if this value is not none, you can return it. Otherwise, you have to go and do the same thing where you check if right child is not none, or if node.right is not none. Sorry. Do this call, store it to a local variable. You'll always be able to return that value. So I mean, it buys you a little bit. You're right, you won't have to pay the cost of putting extra things on the stack just to check that they're none. And so that is a real cost. It is slightly more efficient to do that because you're doing the check whether it's none before you have to, and then we'll be able to kind of remove this statement here. And so it does save you a little bit in terms of what it costs to actually put things on the stack, which costs more space, and generally it costs time to put things on the stack as well. I can't remember how much the nitty-gritty about how much it will cost versus the additional cost of doing more if statements. So they're roughly equivalent. This one is just shorter lines of code, so I wrote it that way. Yeah. And so then we're going to see how can we do this with a stack. How can we do this not using recursion? And so this is where this kind of really stack-based versus recursive-based will actually be more equivalent to each other than the loop-based version we did before. So, does anybody have any ideas about how we might get started? I don't know if I've given you enough information. We'll see. We'll see.
While node is not equal to target.
Okay. There's exclamation points in Python, right? Yeah. So while it's not equal to the target, we want to keep searching. And so, if it's not the target, what are we going to do? And part of this, and so yeah.
If it's, well, it's not the target, then search the left, the next left node, or the, yeah.
And so we want to eventually get to be pointing to the left node.
Yes.
How do we, sorry, I'm going to switch out of asking questions because I can't do this because I didn't give you enough information. We're going to end up using one of the data structures we talked about last time, which is the stack. And we've been talking about down here again to do our stack-based representations. Because when we search the value of the left node, we could do a couple of different things. One, we could just set the node to left. But if we set the value of the node, sorry, if we set node to left, we reach that same kind of problem we came up with over here, where we return the value directly from depth first search recursive, in which we lose the kind of history of where we came from. And so we need to do something that maintains the fact that if this is not what we're looking for, we can redirect to what came before. And so the way the data structure will do that is stack, and we'll pretend we have some function that returns a stack that we called last time. In Python, you can use a list as a stack. And so we'll do that directly here. And so if we have some variable called stack, and we know we're going to want to visit both of the children eventually, or we know that we'll visit both of the children if we don't find what we're looking for, we can then add both of the children to the stack. We'll hit a bug in a minute, but we'll fix it when we get to it. And so once we've added values to the stack, how do we change the value of the node? So what would our stack look like? I'm actually going to change these to make it more insight. Agreement?
Node equals node left. Or node right.
So we don't want to, so we've just created a stack that, let's say we started with 4. We've checked 4 is not what we're looking for. So we've added 6 to the stack. We've added 2 to the stack. And so what might we want to do with this? Or how might this be useful? If we remember that the stack is a last in, first out data structure, so whatever we put on last will be the first thing we would get off of the stack. Yep. And so after creating this, or setting this up, node equals stack, pop, and because we're using a list, we have to say it's the last position. And so this sets the current value of node to whatever was on top of the stack before. And so if that is 2, we kind of go on, and then we store this representation. And so let's say we're looking for 3 again. We would loop up to condition 1, or sorry, we loop into current node being 2. 2 is, the value of 2 is not equal to the target 3. And so we would add both of the children again. So we would add 3, we'll add 1. And then we kind of finish that, and this is in the, we then pop the last node off the stack and use that as the current node, which is 1. And so now we're sitting in 1, and we're kind of wondering where to go next. And here is where we get to the bug. Because if we pass in, or if we put none on the stack, if we put these kind of pointers off into space, into nowhere, this line of code is not set up to deal with it. And so, trying to figure out the best way to rewrite it, given the space constraints. And so we're going to make some squishy lines. I didn't quite leave enough space.
You could just add an if statement at the end of the while loop.
No, actually, that's a good. Yeah, let's do that. Or we can just add a while loop within the while loop.
Or that.
And we can just say, well, node is none. Just keep popping things. Actually, no, that will eventually run off the top of the stack if we never find the item.
I mean, you could just do an if statement and then return. If node equals none. Right?
If node equals none. But so this is that case where we run off the edge here again, and we want to have a way that we still go back to set 3.
Then you just pop off another one.
Yeah. While node is not none. Actually, both of these are going to have bugs. I did not write this out very clearly.
Can't you just do 2 if statements if node by is none, or is not none?
Yeah, but that's not as elegant as what I'm hoping for. Despite the fact I'm writing elegant code with bugs. So, I want to try a couple other things that would work.
Yeah.
And then we might eventually need something like that. But I'm going to try something. I apologize. Well, node is over. And then we have to put an if statement inside. Okay. And so yeah, this is it. We eventually need to make 2 tests. One, we need to make sure that if the node is none, we're not going to try and dereference the node. We're not going to look for the value in none, because this will return an error. But once we're inside, we're not going to append children to a node that doesn't exist. So we'll just kind of do our trick where we pop off the values in the stack. But now we need to have another if statement. So we need to make sure that there's something in there to pop. And so if len stack equals 0, I think there's an empty function which would have been better to use, or if not stack, turn none. Otherwise we'll know we'll be able to pop something off and it'll still be something else. Okay, can anybody still read this? That's impressive. So let's walk through what this does, because now it works. And so we'll go through our example again. We're in case 1, we're at the end of the node. What do? We're on, say, this line. We'll say that the node is not equal to the target, and the node is not none. And so since the node is not none, we'll add both of the children, which are none and none. And then we'll say we keep working, we're not returning none, we're not returning anything, and we keep popping things off the stack. So we pop, first of all, the first none. It's none, so we get to go into the while loop. Because it doesn't pass this check, we get to just pop another one off right away. So we pop one of them off, we get to pop another one off. Do the same set of checks, and eventually we get to pop off 3. Now finally. So now we can say, is this the value we're looking for? Yes. We get all the way through the while loop, and finally return no. I apologize for having that be a little messier than it could have been. But we worked through all the problems. And so let's do this for the case. So this is finally at least a little bit of an example of the fact that this took fewer lines of code to write than this did. And it had fewer cases that we kind of needed to worry about. How do we handle this edge case? How do we handle this edge case? What happens when we reach the end of the node? You know, we needed a line up here to do it, a line up here to do it, and a line down here to do it. And eventually we kept running into these problems, having to handle all these cases explicitly. You could also write explicit tests saying, like, only append the child if the child is not none. In that case, it would have actually been a shorter algorithm if we'd done it. But they're roughly equivalent. At the same time, this is relatively straightforward, easy to see what you're actually doing. And so often if you're interviewers, anything, writing a recursive algorithm is a great way to do it because it's easier to write. That said, you can always mention that you could write a stack-based algorithm, and they're often smaller in space. And so how does the complexity of these two compare? Do they take different amounts of time to run? Well, one of them has to visit any more nodes than the other. No, that is the correct answer. How does the space compare between this like really stack-based method and this really recursive-based method?
Pretty similar. Well, I guess it depends on how big the list is compared to these these temporary suspended functions are.
Stack frames.
Stack frames, thank you.
Yep, and that's exactly the right answer. Both of them use a stack, so both of them require some space, some overhead to store what they've looked at and what they still need to look at. And it does just come down to the question of how big is a stack frame that has to hold a node versus how big is a stack frame that has to hold a function call. Because our function call needs to hold the function, at some pointer to what code is going to get run, the node itself, and then the target. And so generally speaking, your recursive call takes up a little bit more space, and sometimes a lot more space depending on what all you need to pass as variables than a non-recursive version. And particularly if you start adding in kind of this target variable here is a number. It's an integer in this case. If this was some complex data structure that I think we'll cover one in an upcoming class, this can be a significant amount of space just copying and passing around this variable. Or even just kind of references to it could eventually create problems too. Particularly, could change you can't pass references. So this is a not trivial amount of space, and it ends up building up. And so often even in these cases when you're using a true stack that takes up some space, it doesn't take up as much. Later? And so from here, we're going to switch into a different type of search. We're going to switch over to talking about breadth-first search. So conveniently indicate that by changing the D to a B. Now I'm going to change this as well. And so I'm actually going to rewrite this code just the way it was, because the beauty of these two searches is that they're very similar to each other in their implementation, which makes them relatively easy to think about using. And so for breadth first search, instead of going down as fast as we can, we're going to kind of wiggle back and forth, and it's similar to kind of reading left to right, top to bottom. But you could change that around, obviously, if you wanted. And so for that, all we're going to do is we're not going to use a stack. We're going to use a different data structure that we talked about. Does anybody remember what we talked about last week as the opposite data structure to a stack? Instead of a stack, which is last in, first out, we want something that's first in, first out. Anybody remember what this data structure is called? It's called a queue. So we're going to use breadth first search using a queue. And just like all the stuff we had up here, just change the names. And the difference between a stack and a queue is that our queue does not return the last item, it returns the first item. And so if we walk through this data structure again, and what it's doing in this example of code, we're going to say we're looking for position 3. We're going to walk in here. To make it really more equivalent, we have to switch the left to the right. So we're end up, our data structure, I'm going to draw it the same way. Actually, I won't. That's not going to be very helpful. So we're going to end up making a queue. And we're going to have first node that we look at be 4. And 4 is going to add 2 to the queue, and it's going to add 6 to the queue. And we're going to go into position 2. What happens when we get to node 2? What are the actions we end up taking? So we're in this line of code. Where do we go from here?
It's not known, so you add the left and the right node?
Yep, you add the left and the right node, which in this case is 1 and 3. And then what do we do?
Check the next one.
Yeah. And so we erase the node we were looking at, which is 4, and we take the next one in the queue, which in this case comes from the front. So we end up looking, sorry, we've already done that, we're in 2. So we end up taking the next one that is in the front when we're looking at 2, which means we erase 2, and we take the first one here, which is 6. And so now we're searching over here. What do we do when we're here again? We add both of the children, which is, in this case, 5 and 7. And then we pop the value off the front of the queue, and store that, or use that. So now we're looking at 1. And in this case, we add our nones, that the children are down here, to the back of the queue. We erase 1, and we look at 3. And we found our value, and we can return it. And so, yeah, we can eventually find the value we're looking for doing this. And the difference is, to get down to this leaf, we had to look at all the levels in between. And so what is the worst case, or what's the best case to the leaf for breadth first search? to get to a leaf. So a leaf, again, is this bottom row of nodes.
So it's n minus the last row?
Yep.
Minus however many are on the last row.
So it's n over 2.
So the last row ends up being half the size of the rest of the tree. And so it's order n over 2, which commonly gets written order n. And so the best time to the leaf is the same as the worst time to the leaf for depth first search. However, that said, when you actually write algorithms, it's far more common to write best first search than depth first search. And we'll talk about why that is in a second. But we'll get there. That's probably too much of a lead in.
Is the worst the same as the best?
Well, so the worst doesn't have this n over 2 factor.
Right.
However, we can talk about cases also that are not on the leaf.
I mean, why are we evaluating this based on best time to, or based on time to leaf? We should be evaluating it based on time to target, which, depending on the target you care about, could be totally different, right?
So the best time to target for both of these algorithms is the same.
Yeah.
Kind of depending if you kind of scatter it about randomly.
Yeah.
It ends up being, if I remember correctly, it ends up being about n over 2. Maybe it's like n over 4 or something, but it's order n still. And so there's not clear differences on that one, which is why it's not talked about as much. But it's good discussing in which cases it'd be better to use which algorithm. And so we can actually walk through this and ask which cases we expect one algorithm to outperform the other. So if we were looking at the root node, which algorithm does better? Pardon? Yeah, they both have constant time, they both check. Is this the one I'm looking for? Done. If we're looking at the first row, which algorithm do we want to use?
Right.
Why?
Checks both first rather than goes all the way down one and checks the other.
Yep. And so if we're checking the 2 value in this position, they'll both take the same amount of time. We'll both go down to the first one and say, we found it now at this first node. The difference becomes when we're looking for something else on another branch. And so if we're kind of going all the way down the left side, we'll miss that. So we're doing depth first search, it'll take a long time to explore this other position that was very near where we started. And so this is why this is where breadth first search is helpful, because it will explore this thing that's close to it before depth first search is. However, if we're looking for things that we know are in a leaf, and so there are some cases where this can come up depending upon kind of how things are structured in nodes and kind of what's out at leaves. I can't think of any off the top of my head, but it can come up. If we knew what we were looking for is in a node, which algorithm is better to use?
That I guess.
Depth first search. Because at least some of the time, you will get there faster without checking all of the intermediate levels. As opposed to breadth first search, where you're guaranteed to check all the intermediate levels before you start checking the ends. And it's also kind of, what are the costs? If it is really bad to kind of explore the whole space, you want something that every now and then will be more optimal than that. And this is, depth first search will often do that. It tends to get lucky more often, but it's kind of more often explores areas that aren't necessary, depending upon the problem. We'll talk about that more in a minute though, and we'll talk about this. Can anybody think of a breadth first search algorithm that would be recursive? And that silence is appropriate because there's not really a clean breadth first search algorithm that's recursive. I think somebody has published one, but it's really, really ugly. You never want to think about it. It was more just to prove that they could do it. Because breadth first search uses a queue and not a stack, it doesn't have a simple recursive algorithm. And so this is one thing where you can write algorithms that are pretty simple, that are stack or stack-like and use these kind of first in, first out, or last in, first out data structures, but don't have recursive implementations. And so almost everything you can write with recursion, you can write in a non-recursive version, but there are things that you can express non-recursively that are hard to do recursively. You can try it
Just
later.
yeah, I'm
Then
just
send
like,
it to me.
feel like I can do it, but like I can't.
I would say you are welcome to try, and if you come up with it, totally send it to me. I'll be excited to see it. And it is kind of fun to struggle with for a while, and it will teach you something about how recursion works, to kind of grapple with how can we try to get a recursive algorithm that does this search. And so, we'll get there. So it's worth exploring. But generally speaking, if you're trying to do breadth first search, don't think about doing it recursively. If you're trying to do depth first search, it's often worth trying to do recursively because it's cleaner. But let's talk about a case where, so does anybody have any questions on this before I erase it? Awesome. Let's talk about a case where breadth first search and depth first search really end up being very different. And so here we were talking about a tree. I'll leave it up here for a second because it'll come back to the thing we're talking about next. But what happens if we have a graph? What happens if we have things that are like the streets? And so you know you are at Mission Bay, and we are going to go to Golden Gate Park, and we have some address there. And you could say there are intersections kind of scattered throughout the city, and there are streets connecting them. How do these two algorithms perform in this graph situation where you could, that's much larger and less constrained than a binary search tree? And how do these graphs change? And how do we think about these graphs changing? So what's going to happen with depth first search if we start here at this location?
Just gonna pick a direction and go.
Did I say depth or breadth? Say
Depth.
okay, well I'm going to change that. Kind of said that one. So if we have breadth first search, what happens?
Both of them will check themselves first, and then breadth will check all its closest children. So that would give you the shortest path.
Yes, it will eventually return the shortest path. And so it will eventually kind of iterate outwards, testing all directions equally, to kind of give you, and it'll eventually return, when it finds this location, it can return the shortest path to get from point A to point B. How do you need to change the algorithm from what we had written before to deal with the fact that we're in this graph now? So what's kind of one difference between this tree and a graph?
It's not binary.
It's not binary. That's actually, in this case, that's a relatively minor difference. The algorithm handles pretty well both cases.
Would you just add all the children? And then just add all the children's children and check that way?
Yep. And so that's the difference between binary or not. Having just 2 children versus having 100 children doesn't matter too much for this algorithm, or for these types of algorithms.
Oh, this, like that setback.
Yep, that's the one. So the fact that you can go around and around and around in a circle is more than you want to do. Because you're still just kind of looking for kind of a path to get from point A to B, it ends up just kind of being some wasted cycles, and you'll still eventually find that path. But you'll want to check am I just going in a circle? And so you'll want to kind of do something to track the visited nodes, which is good but not required. So now we'll talk about what happens with depth first search. Since you already told this one, do you want to say it again? So what happens if we're trying to do depth first search on a map in the real world with streets?
Or just pick a direction and keep going in the same direction
Yeah,
as far as you can.
you pick some direction. Here we'll pretend I have nodes kind of going out in this direction. There's nothing that makes sure you go towards your goal. There's nothing that prevents you from going the wrong way. And when you do, there's nothing that keeps you coming back or reorients you. There's also nothing that stops you from going around in circles at this thing. Particularly because it's depth first search, if you don't track your visited nodes, and you always take left turns, you're taking left turns over and over and over again, and you're just running in loops. And so here it's good to track your visited nodes. Here it's absolutely required. And the reason it's required is because we have loops. And so this is a case where we have cyclic graphs. If we had non-cyclic graphs, if we had acyclic graphs, then you don't need to track them. And so that could be a bonus in that case.
So, if we're trying to figure out the shortest path, then the actual implementation as compared to the function that we had last time, we wouldn't really care about returning the node per se. We'd want to return the queue, I guess, once you find it.
Instead of returning, so instead it's just a difference of what you put on the queue. What you end up putting on the queue is actually the path up to that point.
Okay.
And so rather than just putting the node that you're visiting, you put the path.
Okay.
Does that make sense?
Yeah.
But yeah. And then if you just keep putting the path down there, you just check if the last point in this path the target.
Right.
If the last point in the path is the target, then you know that there was nothing you could have done that was shorter. But that also brings up a good point. Let's say you did depth first search, and due to great happenstance, you managed to find your target. What's different between the path that you get from depth first search versus breadth first search? It's hinted at by the squiggly line. And something in the sentence you said, or the question you had.
Well, it's just the particular path is just based on the bias that's built into your LIFO structure. It's not based on whether it's actually the shortest path.
Mm-hmm. And so this one has a property that any path you return is shortest path. This one returns any old path that it just happens to find.
Well, it'll return the shortest. It'll return the first complete path. That, let's say the first thing you always look at is the left child. It'll return the first path that has as many lefts as possible or something, right?
That's true, but will there ever be a shorter path than that? It will.
Oh, no, I know. I'm not saying it's a point in its favor, but I'm just saying, it's actually, there is some structure to the choice, right?
Yeah, that is correct. It will tend to think, based on how the binary search works, it will tend to favor at least the very last step that or last two steps. Towards the end, it will favor whichever children are checked first.
Right.
But because you're doing kind of this sweep through all of the spaces, it won't matter too much at the kind of points up here. It'll matter more at the end. That said, it will always be the shortest path. There will not be another one that's shorter that you could have gotten there some other way. And so it might be a little bit biased in terms of what it returns, but it will always return the shortest path. And so it might have some structure in terms of what it returns. And so, let's say, and so these are kind of the basics of what you need to know for an interview. How might you modify, or what information might help you figure out an algorithm that could do something? Sorry. We're going to talk about 2 more cases, and then we'll talk about how we improve it. So under what cases would you want to use breadth first search? We kind of talked about it if you're in like this big unexplored space. What spaces would you want to use depth first search under on a graph?
So you sort of asked 2 questions. Which question are you actually asking?
Fair point. So when you're, let's ask this question. So we talked about breadth first search a bit. Let's talk about a case where you would want to use depth first search.
When you have a lot of nodes. When you have more nodes than you have time to search through all of them.
And why would you? And so why would you want to use depth first search when you have?
Because it's faster. Average time is faster.
Average time is not always faster. If you think about this case where we're doing a map, and you're flying off into space.
Well, no, I mean like average time to search through to find your desired path.
Average time to find any path in a limited set of possible paths. So if the total number of points is small, the average time to find any path in that will be shorter because sometimes you'll get lucky.
If you knew your target was as far away as possible in the graph, then depth first search would be faster.
Yep. And so that's the case, where you know that you're really far away from what you want. And then because then you're going to have to check all of these points to get there, whereas opposed to this case where sometimes you'll get lucky.
It still won't necessarily give you the shortest path. Depth first search will, like, in the sense that it'll give you any path in the sense that it will find the target. But if you're interested in the shortest path, I think breadth first search will still always be faster, right?
Breadth first search will always return the shortest path. Depth first search makes no guarantees about it.
But there's times where you don't need the best, you just need one
Anyway.
that works or like a good enough.
What would an example of that be?
So if you're limited on time and you just need to start doing something because sitting around is going to get you killed, like if you're a mouse or something, you need to figure out where am I going to go if I'm like dropped in the middle of a room. And so you say, well, you know, it's a little dark over there, and if you were to turn around, you might realize that there's a dark spot behind you that's a little bit closer, but the fact that you are standing there thinking about where you're going to go is bad. And so you just need to start running. If all you need to do is start running and start doing something, a depth first search can perhaps give you a goal to move towards quicker. But you're right, it's a somewhat contrived example that doesn't happen terribly often in practice.
Or, if you just need directions, like you need to get somewhere, but.
Yeah. So the problem with that is often that depth first search can have you
Totally.
go into a far off in the wrong place.
But, yeah.
And so it depends how close you are. And there's, particularly for the case of directions, there's an improvement that you can do to get the best of both worlds. And we'll talk about it. It's not something you ever need to know for an interview, generally speaking. If not, you might be able to rederive it on the spot. It's called the A-star algorithm. And it takes advantage of the fact that you have some information about the world, oftentimes. For example, if we're on a map and we're trying to get to here, and we're over here, how much do you really want to consider directions going in the wrong way? And so if you have some information, such as saying, you know, these nodes are perhaps closer or further from the goal, it's called a heuristic. I take that back, sorry. Those are just distances. But you can form what's called a heuristic to say, that you like small distances. And so you can, oftentimes what you do is you can calculate for any node that you're looking at what the estimate of the distance is, plus total distance you've already traveled. And so instead of using a queue properly, we use a priority queue, which we talked about a little bit last time. I think, actually might have just been in the extra credit, which always returns the shortest value you put into it. It's kind of like keeping a binary search tree, but instead of having the root value at the top, you always have the lowest value at the top. And so once you take this off, you'll be able to restructure it so that you get the next lowest value from it easily. And the only thing you keep putting onto it is your estimate of how far away something is. And so your estimate is the estimated distance to target plus the true distance traveled. And so you store this and you just keep looking at whichever one of these has the least. And just like with breadth first search, you keep it in a type of a queue structure. This type is a priority queue that gets you sorted. And you just pull out kind of what you think is there. And so it allows you to kind of avoid this kind of wavefront search that you have to spend a lot of time looking at things out here with breadth first search. And so it has the property of depth first search that'll go towards a target, or that it can quickly go towards a target. But unlike depth first search, it will rarely consider things in the wrong direction. However, if you end up with this big wall in between where you are and where you're going, you'll go towards the wall and then do this thing where you just keep searching, just keep searching, just keep searching, just keep searching until you finally go over the wall and you get to the target. And so you should look up the A-star algorithm because it does some funny things. I think Wikipedia has some animations doing this. Or if not, you should be able to find some other ones online. And there's a number of other kind of variations on this algorithm and similar algorithms for what you can do if you have some information that you can use to form a heuristic.
So, in other words, if breadth first search is like a FIFO structure, depth first search is the last in first in structure. This is just kind of a best in first out.
It's a best estimate first out.
Yeah.
And so that's a priority queue that has that property. It's lowest value first out. You can set up to the max value easily as well. But then it's just kind of a question of what do you store in that data structure. And here you're storing the estimate of distance.
So in other words, like with our DFS that we wrote before, the bias that it always has is like left, right? Like it's just kind of static. And then this is basically DFS, except you kind of have this like intelligent bias as to what like in each iteration, what the first guess would be, what the first thing to look at would be. You know what I mean?
Correct, yeah. And so that's kind of a way to think about it. So it's similar to a depth first search, only you have additional information to make some educated guess.
Yeah.
To have some heuristic rule to say anything that's closer is estimated to be closer to the target, and therefore it's better. There are lots of classes, and often computer science kind of what it pushes forward with is there's types of problems you can't get exact solutions to, or if you do have exact solutions, that are like some pretty slow depth first searches or breadth first searches that have to cover the whole space before they can get there. If you use some heuristic, you can get a better average time. Oftentimes they don't improve the worst case. For example, this A-star algorithm we were talking about, the worst case is still order n, it still has to touch everything. But it's less likely that you hit that worst case. So it's more likely to take a more direct route, but at the same time it requires additional information in terms of the distances or an estimate of the distance, and it requires a little bit more coding to do. And so there's lots of kind of examples of this, but we're just going to talk about that one existing. And so then we'll finish up with a little bit of quick definitions and a little bit of pseudocode, talking about tree traversals, and then we'll wrap up for the day. So I think we're still on slides. We have tree traversal. Everything else was stuff we talked about with breadth first search on a tree and then on a graph. And I'll talk about tree traversals, and you can write them either recursively or stack-based. They're kind of fun to do. We'll just talk about them really quick recursively, because this is an example where some of them are much easier to do recursively than with a stack. And then next week we'll talk about sorting. So with the, so what does it mean to do a tree traversal? It means you go through the tree and you list off everything that's there. And so often it's a case of like, you have a bunch of stuff in a collection or in a tree, in a data structure that looks like a tree. You want to list everything that's inside of it. But how do you want to list it off? You can list it off in kind of 3 easy to describe ways that are common to talk about on trees. There's in order, prefix, and postfix. I think these are sometimes called pre-order and post-order. Doesn't really matter too much. We'll walk through the in-order one, and then we'll talk about how that changes to get pre- and post-order. It's what that means, what in-order means is that for a binary search tree, you would list them off in numerical order. And so this is how you can convert a binary search tree to an array that has less memory overhead, but maintains its sorted order. And you could do it in order n operations. And so, actually, we're going to write up the code, just because. We need a global pointer. And so, if we want to visit things in order, how do we do that? What's the first? So we're starting from node 4. How do we add something to put it in order? Don't write that on code out, but you could. So what would we want to do? If we start here, we want to go left. And since we're doing things recursively, we're just going to say in order with current, sorry, this is current node, should have done that better. Current node.left. However, we're finally going to take Ken's suggestion, and we're only going to do this if current.left actually exists. If it's not none, then we'll go and go down current.left. So we've gotten all the way down to current.left, farthest left corner we could get. What do we want to do to this? If we want to, let's say, return it, append it to our list. Yeah. We want to put it in a queue, or in this case, a list will also serve as a queue. And then what do we do? Try to go right. And so this will give you everything in order. And it's relatively straightforward. These are a little more complicated to do with a stack. So I encourage you to give that a try if you want some practice. Any ideas how, given that there's a name called pre-order and post-order, how you might change this to get one of these things with one of these names? Exactly. So the difference between in order, pre-order, and post-order is just where you put this append. Oftentimes it can be a print statement, or it can be evaluate, or it can be whatever processing you want to do on it. But when you do the traversal, it's just kind of choosing where you do that check. And so if you put it, let's walk through the different cases for what will get printed off. If we print them off in order, it goes 1, 2, 3, 4, 5, 6, 7. If we go pre-order, what are we going to print off? 4.
2, 1, 3, 6, 5, 7.
Well done. Post order?
1, 3, 5, 7, 2, 6, 4.
Yes.
Pretty sure. Or it's
Did I do that right? You go down here, we'll print this guy first, we'll print this other child, we'll do 2. And then we'll touch this guy's, will be in this node, and we'll print off its children. 5, 7, then 6, and finally 4. Part of the reason for knowing these is just because somebody might ask you them. There are times when it actually matters, but they're kind of use specific. They're kind of knowing that you can just take a very simple algorithm and moving one statement can change the behavior of it pretty drastically is the kind of goal of what to understand. And I encourage you, if you want to see it as a challenge, is some of these are much, much easier to implement with a stack than others, or with a stack or a queue or appropriate data structure. And so trying to do all those can give you an intuition for how nice it is to have recursion in some instances, and how much a pain in the butt it is to do without sometimes. But for that, I think we'll probably end for this week, and we'll do sorting next week, and then hopefully get on to finish enough stuff that we can do the last example. Otherwise, we'll do that in one more week. Although,
2 weeks, right?
yeah, I was going to say, I will not be here in person next week, so we'll actually have it be 2 weeks from now will be our next class, and I'll send out an email about that. Any questions before we go?